Students, hi students. In this lecture, I am going to discuss previous IT problems. See, first one, two vehicles each moving. So given two vehicles each moving with a speed u on the same horizontal straight road are approaching each other. Wind blows along the road with velocity w. One of these vehicles blows a whistle of frequency f1. An observer in the other vehicle hears the frequency of the whistle to be f2. The speed of sound in still air is v. Correct statements are, so this is 2013 advanced problem. So given two vehicles moving with a speed u on same straight road approaching each other, and wind blows along the road with velocity w. So one of these vehicles blows frequency f1. Another vehicle now it is observing this frequency, and that is to be given as f2. So we have to see options, right? See first option, if the wind blows from observer to source, so relation between f1 f2. Wind blows source to observer, again relation. That means we have to focus wind blowing observer to source, source to observer, then relation between f1 f2, right? Let us see how to verify these options. Right, we are given, two vehicles, they are moving. You can say vehicle 1, vehicle 1, and this is vehicle 2 moving towards each other, and frequency of, so one is now emitting sound. Let us say this is now source. This is now source, and this vehicle is now listener. Okay. So frequency of this vehicle is f. Okay. Now frequency observed by this vehicle is f2. Right. Now cross check. First of all, take the first case, that is wind blows from source to listener, means like this. And given velocity of wind is w, and velocity of a sound is given as v, right? And velocity of each vehicle given as u. This is u and this also u. Let's see how we are solving it. So first of all, find velocities with respect to medium. That means velocity of source. So wind is now from source to listener, right? So velocity of source, I'm writing here velocity of source, that is equal to u minus w, that is vs. Velocity of listener, velocity of listener with respect to medium, it is, with respect to medium, it is u plus w. Okay, right? So we got velocity of a source and velocity of listener with respect to medium. Now coming to our result, so we have result, that is frequency observed. Frequency observed is equal to original frequency f1, right? velocity of sound, that is given as v, that is v. So velocity of listener is now u plus w, and that is now towards the source. That is now towards source, right? So we have to write here v plus, it is a plus u plus w, right? Dividing with v, we can see source moving towards listener. Source moving towards listener means he has to get more frequency, right? So denominator must be less. So we are writing here minus u minus w. Okay. So this is now expression for F2, right? Now see, is it greater than F1 or less than F1? So this is now V plus U plus W. But this is V minus U plus W, right? That means denominator is now less. What is it? Denominator is now less. Denominator is less means now this value greater than 1. So this is greater than 1. So this is greater than 1 means F2. F2 is now greater than F1, right? So see carefully once what we got here. V plus U plus W. This is V plus W minus U. So this value is greater than 1. So this is greater than 1 means F2 greater than F1. So here what we can write, F2 greater than F1. That means when wind blows, from source to observer, source to observer, F2 is greater than F1, right? Okay, now verify the next option. That means, right, now let us consider, the wind blows in reverse direction. That means source, listener. Now wind is blowing listener to source. Okay. Right. Now see what happens. Coming to here, U, and this also U. Next, wind is blowing like this. First, I'm writing their velocities with respect to medium. So Vs equal to velocity of source with respect to medium. It becomes U plus W, velocity of source, right? Next, coming to velocity of listener. Velocity of listener will be U minus W. So these are velocities with respect to medium. Now substitute these values. See what we get. F2 equal to F1 into, you can see listener is moving towards the source. So we have to write V plus U minus W in the place of V. And next this is source moves towards a listener. So it is V plus, it is U plus W. Wait, here I have to make a small correction. That is, this is not plus. because source is moving towards listener, so it should be minus. Okay, right. Now you can see V plus U minus W, but this is V minus of U plus W, right? That means once again denominator is now less than numerator, therefore this value is greater than 1, means again F2 is greater than F1. That means whether wind is blowing from source to listener or listener to source, okay, frequency will be greater than the actual frequency. Are you getting it? In both the cases, observed frequency is greater than the original frequency. I think here we can get the same conclusion without making calculation also. The reason is that here source and listener both are moving towards each other. In such a case, whether we take from ground frame or with respect to medium, in both the cases, result will be same. So since both are moving towards each other, he observes more frequency. So this is by making calculation, we are getting answers, but same conclusion we can get without making calculation also, because they are moving towards each other. So definitely he observes more frequency. Okay, right. So options are if wind blows from observer to source, F2 greater than F1. Wind blows from source to observer, F2 again greater than F1. So options are A and B, right? See next problem. A person blows into open end of a long pipe. A person blows, I think it is air, okay? A person blows air into open end of a long pipe. As a result, a high pressure pulse of air travels down the pipe. A person blows into open end of a long pipe. Blows open end of a long pipe. As a result, a high pressure pulse of air travels down the pipe. It is high pressure pulse. When this pulse reaches the other end of the pipe, so this is IIT 2012 year advance. Right, see options given. A high pressure pulse starts traveling up the pipe if other end of pipe is open. See next option. Low pressure pulse starts traveling up if other end of the pipe is open. Next given closed and closed. Let us see what we have discussed a concept earlier. Just revise briefly once. So we have discussed the concept like open end acts as a so this open end is a pressure node and closed end is a pressure antinode. So when there is reflection at pressure node, when there is a reflection at a pressure node, that means open end, there is a phase change of pi. Phase change of pi means now here high pressure reflects as high pressure pulse reflects as low pressure pulse because open end is a pressure node. There is a phase change of pi. Therefore, high pressure pulse reflects as low pressure pulse at open end. If you take closed end, pressure anti-node. There is no phase change. No phase change means high pressure pulse reflects as it is high pressure pulse. There is no phase change. So this is what earlier we have discussed, right? Reflection from open end. Compression comes as rarefaction. Rarefaction reflects as compression. Closed end, that is pressure antinode. There what happens is compression comes back as compression. Rarefaction reflects as rarefaction. Now using here same logic, see options. Coming to first option, high pressure pulse starts traveling up if other end of the pipe is open. Open means pressure node. That means we get low pressure pulse. So A is not correct. Right? B. Low pressure pulse starts traveling up if other end of the pipe is open. This is correct option. Because other end is open means pressure node. There is a phase change of pipe. That means high pressure pulse becomes low pressure pulse. Right? Okay. Next, coming to closed one. Coming to closed one, there is no change. That means high pressure pulse starts traveling up if other end of the pipe is closed. Because in this, there is no change of phase. So options are D is correct and B. So B and D are correct options. Okay, right. See next problem. A train approaching a hill at a speed of 40 kmph sounds a whistle of frequency 580 Hz. 580 Hz when it is at a distance of 1 kilometer from a hill. It is given a train approaching a hill. Speed is 40 kmph and frequency 580, right? When it is at a distance of 1 kilometer, right? Distance given 1 kilometer. A wind with a speed of 40 kmph is blowing in the direction of motion of a train. So wind speed and train speed both are same. Okay. Then we have to find frequency of the whistle as heard by an observer on the hill. And next one, the distance from the hill at which the echo from the hill is heard by driver and its frequency. So this is a previous IIT 1988 year given for 5 marks. See first what we have to calculate frequency of the whistle as heard by an observer on the hill. Next one, distance from the hill at which the echo from the hill is heard by the driver and its frequency. Given velocity of a sound in air 1200 kmph. Right? Okay, see how we start the problem. First of all, write down the given data. So train is approaching a hill and this is a hill. Okay, that is a hill. I can tell like this. That is a hill. A person sitting on the hill. So frequency observed by him. Given train velocity 40 kmph. Wind is blowing Wind is blowing with the same velocity in the same direction, right? And given velocity of a sound 1200 kmph, and coming to frequency given, it is a 580 Hz. So this is now given data. So we have to find frequency observed by a listener on the hill. So first of all, we calculate velocity of listener, velocity of source. We can see velocity of source with respect to wind is 0. So V is 0. Next, VL, velocity of listener. With respect to wind, velocity of listener is 40 kmph and direction is, it is left side. That means question is like train is stationary, train is stationary, listener moves towards train. Okay. Then see frequency observed by listener. So take it as F equal to F naught. Listener moving towards stationary source because Vs equal to 0, right? Speed of a sound 1200. He is moving towards a source plus 40. Okay. Source is not moving. It is 0, right? With respect to medium. So it is now 1200. Therefore, answer is now, it is approximately 600 Hz. Okay, now approximately, right? So first we are finding velocity of source and velocity of listener with respect to medium. Now putting values in that. Okay, right. Now coming to the second question. Second question, he is asking at what distance from the hill he hears the echo. Let us take now this is a hill. That is a hill. At a distance x from hill, now he hears echo. Okay, distance is x, right? And you are given distance equal total value 1 km, right? When it is emitting sound. So total distance is 1 kilometer. Then see what happens. Once a sound comes outside, this has to cover 1 kilometer. Next, again, while coming back, it has to cover x distance, right? Then see time taken. See what taken that time taken. So time taken by sound while traveling 1 km, that is 1 km by velocity will be, velocity will be, velocity of sound is now 1200 plus 40. This is velocity of sound in ground frame, right? 1 km. While coming back, it has to cover x distance, traveling opposite to wind blow. So it becomes now plus x by 1200 minus 40. So here we have taken wind velocity in the ground frame. Okay. So in this time, what happens is source covers, means train covers distance 1 minus x, right? In the same time. In the same time. So we are equating now the time taken, right? Equating time taken. So it is now 1 minus x, 1 minus x, and velocity of train is 40 kmph, which is a constant. So what we are doing here, We are equating time taken by train to move from here to here. In the same time, sound travels from here to up to hill and comes back same time. So we are equating times. Okay. Now, if you simplify this, so we get x value approximately 0.935, approximately 0.935 kilometer. Okay, that is the distance from the hill where the driver hears echo. Okay, next. Okay. Now we have to calculate what is the frequency observed by the driver. What is the frequency observed by the driver? See how we calculate that. Frequency observed by the driver. So in the first case, we got frequency observed by the person sitting on the hill, right? Now that hill becomes as a source. What is it? Hill becomes as a source and driver becomes now listener, right? Therefore, I'm calculating here first of all velocity of source. Velocity velocity of source equal to, now in this case, source is a hill because sound reflecting from the hill, and hill velocity with respect to medium is 40 kmph with respect to medium, and direction is, see, it is left side, right? And with respect to medium, velocity of listener means train driver, it is zero. That means a source moving towards stationary listener, right? Then write this frequency as f dash equal to f into, right? Now velocity of a sound, that is 1200. Coming to listener, he is stationary, so zero. But source is moving towards the listener. Source moving towards listener. So it becomes now 1200 minus 40 because moving towards listener, that is equal to, that value we got is 600, and this is now 1200 by, this is how much, 1160, right? And if you simplify, we get approximately 621 H approximately. Okay, so this is the question. I hope you got a clarity. So one thing we have to keep in mind, we are taking all velocities with respect to medium. Okay, no? Right. Good. Now see next problem. See, a boat is traveling in a river with a speed 10 meter per second along the stream flowing with a speed 2 meter per second. From this boat, a sound transmitter is lowered. From this boat, a sound transmitter is lowered into the river through a rigid support. The wavelength of the sound emitted from the transmitter inside the water is 14.45, and given this mm, right? Right. Assume that attenuation of a sound in water and in air is negligible. And we can say this question is given for 10 marks in 2001. Okay. Let us now focus carefully how we are starting the problem. Right. First, see what we have to calculate. What will be the frequency detected by a receiver kept inside the river downstream? Condition is given inside now downstream. Right. Okay. And next, see what we have to calculate in that. The transmitter and the receiver are now pulled up into air, and air is blowing with a speed 5 meter per second in the direction opposite to the river stream. Determine the frequency of the sound detected by the receiver, right? Temperature of air 20, density of water given, bulk modulus, gas constant, mean molecular mass of air, and we are given Cp by Cv also, right? So first we have to think like this. What is the purpose of giving bulk modulus and what we call density of water, right? So purpose of giving these two is speed of speed of sound in liquid, right? What we are given here, wavelength, right? 14.45 mm. So first focus, what will be the frequency detected by a receiver kept inside the river downstream? Speed of boat 10 meter per second, and stream flowing now 2 meter per second. So both are given in ground frame. Okay, both are given in ground frame. See how we solve the problem. Right. So first we are focusing on write down the given data. It is given that transmitter is now in the river. So it is medium is now river. Velocity of boat and velocity of a transmitter both are same, 10 meter per second. Velocity of river 2 meter per second, right? And we are given that there is a receiver, right? There is a receiver, a receiver kept downstream. That means if this is a boat, this is now receiver. Okay, right. Medium is now water. Let us calculate what is Vs, velocity of source. Now boat is source, right? So velocity of source with respect to medium, that is 8 meter per second. Okay, and that is now right side, means towards the receiver. Coming to velocity of listener. Now listener is nothing but receiver. Its velocity with respect to river. River is now flowing right towards right side, that is we are. With respect to river, his velocity will be left side. So his velocity 2 meter per second, it is left side. So question is just like both are moving towards each other. Both are moving towards each other with velocities 8 meter per second and 2 meter per second. Right? Now take the relation that is F equal to F naught into V plus or minus VL by V plus or minus Vs. Okay. Now substitute value in this. And before making this calculation, first calculate what is the value of V. V value in river, right? inside liquid is root of B by rho. B by rho, right? And we are given bulk modulus, that is, the bulk modulus how much given? Bulk modulus is 2 point, bulk modulus is 2.088, 10 power 10 power 9 Pascal bulk modulus. Density of water is, see how much given? It is given density of water is 10 power 3, right? 10 power 3. So from this we are going to get speed of a sound in river medium. What is it? In river medium. And see that value comes out to be how much? It comes out to be 1445 meter per second. And remember, this is velocity of a sound with respect to river. Okay. Now substitute this value in the above one. Next, one more thing we have to focus. What is F naught? Okay. To get F naught value, we are given F naught equal to V by lambda. V value 1445. Lambda already given. Lambda given 14.45 mm, right? This is mm. Okay, no? That means frequency will be 10 power 5 H, right? So it is given speed of a sound with respect to river is 1445, lambda given, therefore frequency 10 power 5. Now substitute these values in the above one. 10 power 5, we got velocity, it is velocity of a sound 1445. Listener moves towards the source. Therefore, we have to write it is now plus 2. Next, 1445. Source is moving towards listener, right? So we have to take here minus. It is -8. So see the calculation, what how much we are going to get. So this value will be, see, approximately 1 point, approximately 1.0069 10 power 5. Okay, this is the answer, right? See here what we have done. So we have taken, first of all, velocity of a sound with respect to medium, 1445 meter per second. And we got frequency 10 power 5 H. Next, we got velocity of source with respect to medium, 8 meter per second. Velocity of listener, here listener means receiver, with respect to river, 2 meter per second left side. Okay, this is the first part. Okay? Let us see one second part. So first part over at A is over. Second part. The transmitter and receiver are now pulled up into air. The air is blowing. With a speed of 5 meter per second in the direction opposite to the river stream. So condition is air is blowing with a speed 5 meter per second in the direction opposite to river stream. Determine frequency of the sound detected by the receiver. Temperature of air and water 20 degrees centigrade, density given, temperature given, density given, mean molecular mass is given and are also given. And you are given Cp by Cv also. Cp by Cv also. So observe that why we are given temperature, next gas constant, mean molecular mass and Cp by Cv means gamma value. That means we have to find the speed of sound in air that we have to calculate. Okay, right. Let us see how we solve the problem. What is this? Right. See now, first of all, what we have to calculate. First condition, the transmitter, right? Transmitter moving like this. Receiver stationary. You can see this is now liquid, okay, which is a flowing. Now they are outside liquid, okay, outside liquid. Transmitter velocity is given boat velocity, right, 10 meter per second. And wind is blowing opposite to river flow. That is given 5 meter per second, right? Okay. That means from this what we are going to get? Velocity of source. I'm writing here velocity of source with respect to medium. With respect to medium is now 5 meter per second and direction is right side. Direction is right side. Next, velocity of listener. Listener velocity, it is a 5 meter per second. It is left side. That means they are moving towards each other with the same speeds. Okay, with respect to medium. So first I'm calculating what is velocity of a sound in air medium. That is equal to root of gamma RT by M. Gamma RT by M. Gamma value given, R value given, T value given. So T we have to take in absolute scale, means Kelvin, and mean molecular mass, right? So by substituting all these values, this speed comes out to be 344 meter per second. Okay, right. And coming to frequency, we are knowing that frequency is independent of the medium. Therefore, F naught, it remains 10 power 5, right? 10 power 5 H. This is what we got in the above problem, right? Now calculate frequency observed. So take it as F dash. F dash equal to F naught into velocity. Velocity of sound 344 with respect to medium. Listener is moving towards the source. Listener is moving towards source. Just a minute. What we have taken. Listener. Wait. Wind is blowing towards. Okay, we have taken wrong thing here. Wind blowing towards the left side. That means velocity of source becomes 15. 10 plus 5, 15. And velocity of receiver becomes 5 meter per second. This will be right side, okay? Because wind blows opposite to river flow. Wind blows opposite to river flow. Opposite to river flow, right? Therefore, we have to write here minus 5. dividing with 344. You can see source is moving with a velocity 15 meter per second towards listener. So I am writing here, it is minus 15. Okay. So after simplifying this value, approximately 1.0304 into 10 power 5 H, right? So this is a way of making the calculation. Okay. So I hope you got a clarity.